in this example, we want to show that the series 1 over n times n plus 1 is convergent and find its sum. Looking at it the way it is, it's not entirely clear how to find the sum of the series. But there's a trick that we can do which will allow us to find an easy formula for the partial sums of the series. And this is called what we'll call a telescoping sum, because as we'll see, when we write out the terms of the partial sum, it will collapse down into a very simple, easy to find formula. However, before we get to that, we need to do something first with the nth term formula here, which is we need to first express it as a difference of two terms. And that's going to be possible when we use partial fractions. So here I'm going to do partial fractions on the nth term. And when we do that, we can then think about what the partial sums of the series are. So we know the form of the partial sums will be a over n plus b over n plus 1. And then clearing out the denominators, I have 1 equals a times n plus 1 plus b times n. If I substitute n equals 0 into the equation, I get 1 equals a times 1, and then the b term would be 0, so it's just giving me a equals 1. If I substitute n equals negative 1 into the equation, then I get 1 equals negative b. Notice that the a term becomes 0, and so it gives me b times negative 1 is negative b. So I have b is equal to negative 1. And so the partial fractions here give me 1 over n minus 1 over n plus 1. Okay. And so the series is in fact the sum of 1 over n minus 1 over n plus 1. Now, in order to find the sum, I'll look at the partial sums of the terms of the series now that it's written in this form. So here, let's look at the partial sums. S1, of course, is just the first term. Notice that's going to be 1 minus 1/2. S2 is the second term. That's going to be 1 minus 1/2 plus, and then when n equals 2, 1/2 minus 1/3. And what I observe here is that we already get some terms that cancel. And so this collapses into 1 minus 1/3. Let's try S3, which will be adding up 1 minus 1/2 for the first term, 1/2 minus 1/3 for the second term, and then 1/3 minus 1/4 for the third term. When I simplify this, 1 minus 1/2 plus 1/2 cancels. Minus 1/3 plus 1/3 cancels. So again, this formula collapses down into just 1 minus 1/4. So noticing this simplification pattern, let's see, what would it be if I were to write out the nth partial sum? So assuming we were to continue this pattern out to the nth term, well, I notice here that the same pattern of cancellation would happen here. Minus 1/2 plus 1/2 cancels. Minus 1/3 would cancel with the plus 1/3 in the next term. And here the plus 1 over n would cancel with the 1 over n minus 1 over n in the previous term. So again, this Sn formula here just collapses down into 1 minus 1 over n plus 1. Now with this very simple Sn partial sum formula, I can find the limit as n goes to infinity, and that will tell me the sum of the series. So taking the limit as n goes to infinity of Sn, we can get the sum of the series, in this case, 1 minus 1 over n plus 1 as n goes to infinity, becomes 1 minus 0. So the sum of the series is 1. So what we notice about this particular type of series is that when we have a difference of terms like we see here, 1 over n minus 1 over n plus 1, we get this cancellation pattern that occurs when we write out the partial sums. So because it's a difference between two consecutive terms, then that cancellation will occur. So you can oftentimes look out for that when you see an nth term that looks like this, where it's a difference between two consecutive terms of a series. Notice that the way it was written originally, it was not entirely obvious that would happen, but it was a little more clear after we wrote the partial sums or the partial fractions of the terms. In this example, we want to show that the harmonic series is divergent. So the harmonic series is this specific series, 1 over n. Notice that it's just summing up fractions, 1 plus 1/2 plus 1/3 plus 1/4, and so on. To show that it's divergent, what we can try and do is come up with a way to show that the partial sums are going to go to infinity. And there's a pretty tricky way to do it. So the way I'll do it is I'll focus on a particular subset of the partial sums. So let's just look at partial sums of the form s2 to the n. And we'll see why we're looking at partial sums of this form in a moment, but it's going to have an easy way of determining how these simplify. And let's take, for instance, s2. We know this is going to be 1 plus 1/2, which is 3/2. That's s2 to the 1. What's s2 to the 2? In other words, s4. 1 plus 1/2 plus 1/3 plus 1/4. So what I can do here is, instead of putting 1/3 here, I can replace that with something bigger. I'm going to replace 1/3 with something, replace it with something smaller. In this case, 1/4. So 1/3 gets replaced with 1/4, and I get something that's smaller. Smaller. Other way around. Okay. So then I have 1 plus 1/2, and then 1/3 becomes 1/4, so that's 1/4 plus 1/4. And why am I doing this? Well, we'll see in a moment, but in this case, notice now that becomes 1/4 plus 1/4 is 1/2, right? And then I can add that with the 1/2 here. So this is equal to 2. Okay. Let's look at s2 to the 3rd. In other words, this is s8. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Okay, so I'll do the same thing that we did with 1/3. I'll replace 1/3 with 1/4. And then I'll replace all of these guys here with 1/8. And again, what that does is it makes the whole thing smaller. So I got 1 plus 1/2 plus 1/4 plus 1/4. And then replacing all these with 1/8. This is now 4/8, which is 1/2. So we got, this is 1/2, and now this is 1/2 as well. So we got 1 plus 1/2 plus 1/2 plus 1/2, and so that would be 5/2. Maybe you're starting to recognize a pattern, right? When we did this one was really 4/2. So 3 halves, 4 halves, 5 halves. You can guess what the next one will be. If I do 2 to the 4th, we can do something similar, right? This is 1 plus a half plus a third plus a fourth. This is 16, so this will go all the way out to 1 over 16. And I can say that this is greater than 1 plus a half plus a fourth plus a fourth. And then replacing all those with 1/8 like we did last time. And then all the ones after that I'll replace with 1 over 16. And there will be exactly 8 of them, 8 of those terms. So this will add to a half, this will add to a half, and then 16, there's going to be 8 of these terms that say 1 over 16, so those will also add to a half. And so this will be 6 over 2. So in general, what we've shown is that s2 to the n is going to be greater than or equal to n plus 3, or no, n plus 2 over 2. Right, so we can kind of see that pattern here. When n was 1, this was 3 over 2. When n was 2, this was 4 over 2. N was 3, this was 5 over 2, and so on. And what we've shown here is that the limit as n goes to infinity of s2 to the n has to be greater than or equal to the limit as n goes to infinity, n plus 2 over n, or over 2. And as n goes to infinity, this will go to infinity. So we've shown that this limit here, and notice this is actually a subsequence, or a subset of the sequence of partial sums. So if the subset goes to infinity, then the actual limit of all the partial sums must also go to infinity. So this is a very tricky way of doing it. We'll see that in another section that there's perhaps a much simpler way to show this when we look at the integral test. In other words, I can compare the series 1 over n with the function 1 over x and think about how it relates to the improper integral of 1 over x. So that will be in the section when we talk about the integral test. But what we can do is mostly just take this as a fact. We don't necessarily need to know how to prove it, but if I know now that the harmonic series is divergent, that's going to be a very helpful fact. And in fact, it might be a little bit like a not so obvious thing here, because it looks like the terms of the series get pretty small, right? If n goes to infinity, the terms of the series are getting really, really small. But in this case, they're not getting small enough that would make it so that this series converges. The series, if I sum up infinitely many terms, is just going to get a sum that grows larger and larger and larger.